Ever wondered what the real difference is between a simple flicker of the lights and a citywide blackout? Well, a lot of the time, it comes down to just a few milliseconds and a really critical concept called transient stability. Today, we're going to dive deep into the physics that keep our world powered, especially when the grid gets pushed to its absolute limit.
At its heart, the power grid is just this massive, continent-sized balancing act. Generation has to equal demand every single second. But what happens when that perfect balance is completely shattered in an instant?
I want you to picture this. A lightning strike hits a major transmission line. In a fraction of a second, the whole system is shoved right to the brink of collapse. The ability to just survive that shock, to stay synchronized and prevent a cascading failure, that's what transient stability is all about. It's like this invisible shield that protects all of us from a total system collapse.
Okay, so here's our game plan. We'll start by looking at the core fight for synchronism. Then we'll unpack the key tool engineers use to figure out the winner. It's called the equal area criterion. From there, you'll see how it becomes a literal race against time, and finally, we'll look at how we actually engineer resilience right into the grid itself.
First up, the fight for synchronism. And this really is the heart of the whole thing. See, every single generator on the grid has to spin in perfect lockstep with every other one. If just one of them falls out of sync, it can start a domino effect that brings everything down.
So that's the textbook definition. Now, it's really important to know where this fits in. Power system stability has a few different flavors, right? You've got voltage stability, which prevents voltage collapses, and you've got frequency stability, which keeps the system at a steady 50 or 60 hertz. Transient stability is a type of rotor angle stability, and it's all about surviving those big, sudden shocks like a nasty three-phase fault.
To really understand this fight, you've got to know the two main forces going head-to-head. Think of it like a giant tug-of-war. On one side, you have mechanical torque, or TM. That's the raw power from a steam turbine pushing the generator's rotor, always trying to make it go faster. And on the other side, you've got electrical torque, or TE. That's the electrical power being sent out, which acts like a brake on that rotor. When the system is stable, these two forces are in a perfect, delicate balance. And the difference between them? That gives us the accelerating torque. It's super simple. If the mechanical push is stronger than the electrical brake, the generator speeds up. If the electrical brake is stronger, it slows down. This one little equation, believe it or not, governs everything that happens next.
So what can possibly break this perfect balance? Well, any number of big events. The most common one by far is a short circuit, what we call a fault. But suddenly losing a huge generator, or a major transmission line, or even just starting up a massive industrial motor. Any of those can be enough to kick off this whole battle for stability.
Okay, so how in the world do we predict if the system is actually going to win this fight? That brings us to the core analytical tool for this whole problem, the equal area criterion. Now this graph, this is the key to everything. It's called the power angle curve. All it does is plot the electrical power a generator can push out against its rotor angle. You'll notice there are two different curves. That top one, that's our healthy system, and we're just cruising along at point A. The lower curve shows what the system is capable of after a fault gets cleared. This graph is basically our playbook. And bam, a fault hits. Instantly, our operating point drops from A down to B. Now look closely. Our electrical power output, TE, has basically collapsed to almost nothing. But the mechanical power, TM, hasn't changed. So now TM is way, way bigger than TE, and the rotor just accelerates like crazy. As it speeds up, its angle increases, and we travel along the curve from B to C. All that kinetic energy it gains during this acceleration, that is area 1.
Then right at point C, the breakers trip and clear the fault. So we jump up to our post-fault curve at point D. And check this out. Now our electrical output T is much stronger than the mechanical input TM. This creates this incredible braking force, and the rotor starts to decelerate, trying to shed all that extra kinetic energy. This decelerating energy is what's represented by area 2, as the rotor swings from D over towards E.
So here it is, the moment of truth. For the generator to stay in sync, the braking energy of area 2 must be big enough to cancel out the accelerating energy of area 1. That's the rule. If it can absorb all that excess energy and wrestle the rotor back under control before it swings too far, the system is stable. But if area 1 is too big, the rotor will just overshoot, and you lose synchronism. It's that simple.
And this all brings us to a really crucial point. This whole thing is a race against time.
See, the longer a fault stays on the system, the more energy gets pumped into that Area 1, which makes it harder and harder for the system to recover. And this defines the concept of critical clearing time.
The critical clearing time is the absolute deadline. It is the maximum amount of time a fault can exist before that accelerating Area 1 gets so huge that no amount of decelerating Area 2 in the universe can stop it. It is literally the point of no return for the grid.
Just look at this timeline. A fault hits. If your protection system is lightning fast, I'm talking Zone 1 protection, clearing it in maybe 80 milliseconds, less than a blink of an eye. Area 1 stays nice and small, and the grid recovers. Stable. But what if there's a delay? What if it takes 150 milliseconds? Well, that's more than enough time for Area 1 to grow way too large. The system just can't recover. It goes unstable. That's the difference. A few dozen milliseconds decides the fate of the entire grid.
So, knowing all this, how do we actually engineer the grid to always win this race? Well, that brings us to our final section, engineering resilience.
Luckily, we engineers have a whole toolbox to improve transient stability. The most obvious one is just faster protection systems, relays and breakers that can clear faults in just a few cycles. We can also do things like reduce system reactance, improve the response time of automatic voltage regulators and governors, put in emergency load shedding schemes, and even install special devices called power system stabilizers that are designed just to damp out these oscillations.
And this all comes back to a core design philosophy, you know? We don't just wait for a blackout to happen and then react. We proactively design and operate the system to withstand a specific list of credible, severe events. We literally plan for the worst-case scenario.
And that is precisely why these studies are so unbelievably important. When you build a model in ETAP or DieSilent or PSSE, and you run a simulation of a three-phase fault, what you're really doing is calculating these power angle curves. You're determining that critical clearing time, and you are verifying, with data, that the protection you designed is fast enough to keep the lights on. It's all about making sure that when the absolute worst happens, the system is resilient enough to fight through it and stay stable.